This video is going to give an introduction to polynomials and how to create graphs of polynomials. So let's first consider power functions, which are functions that just have one term, x to a power. So on the left, I have graphed in green, y equals x squared, that's our basic parabola. In orange is y equals x to the fourth, and in purple is y equals x to the sixth. All of these power functions have even powers, and they all have a pretty similar shape where both ends of the graph are going up. The only difference is, as the exponent gets larger, the ends of the graph get a little bit steeper, and the middle of the graph gets a little bit flatter. We see a similar pattern if we look at the graphs on the right of the screen. These are all power functions with odd powers. In green is y equals x to the third. That was one of our toolkit or parent functions. Right side goes up, left side goes down. We see the same shape when we graph x to the fifth and y equals x to the seventh. Again, a similar pattern is happening here, where as the exponent gets larger, the graph gets a little bit steeper at the ends and a little bit flatter in the middle. So this is going to be our basic starting point for working with polynomials. Notice that when we have an even power, both ends of the graph go up, and when we have an odd power, the right side goes up and the left side goes down. Now, when we talked about graphing transformations, we learned that if we were to just put a negative in front of these, that would flip the graphs upside down. It would reflect them over the x-axis. So let's summarize this information. It turns out that the end behavior of a polynomial, so the graphical behavior where the arrows are, the ends of the graph, is determined by the leading term of that polynomial. And we'll do some examples in a minute, but the leading term of a polynomial is the term with the largest exponent. So the term with that largest exponent is going to dominate what happens at the ends of the graph. And there's 4 different situations that can happen. I have all 4 listed on my slide, but let's run through each one. If the leading coefficient is positive, so the number in front is positive, and the exponent is even, that would be something like 2x to the fourth. So coefficient is positive, exponent is even. We are going to see both ends of the graph going up. We can describe that in mathematical notation by saying as x goes to infinity, so that is talking about the right side of the graph, as x goes to infinity, f of x, the y values go to infinity. That's just a mathematical way of saying on the right side of the graph, the arrow points up. As x goes to negative infinity, that means the left side of the graph, f of x goes to infinity, the graph goes up. So positive coefficient, even exponent, both ends go up. Now, if the exponent is even but the coefficient becomes negative, that's going to reflect the graph, and the graph is going to open down. An example would be the function f of x equals negative 3x to the 6. Coefficient is negative, the exponent is still even. Both ends are going to go down. Again, we can think of this as a reflection. And here's my mathematical notation. As x goes to infinity, so on the right side of the graph, f of x goes to negative infinity. The arrow goes down. As x goes to negative infinity, f of x goes to negative infinity. On the left side, the arrow goes down. Okay, so even exponents, either both ends go up or both ends go down. If we have an odd exponent and a positive coefficient, so that would be something like x cubed, the right side goes up and the left side goes down. So as x goes to infinity, f of x goes to infinity. As x goes to negative infinity, f of x goes to negative infinity. The left side goes down. Finally, our last case, the last possibility we might have, is what if we have that odd exponent, but now our coefficient is negative. That's going to take the graph and reflect it over the x-axis. So an example would be negative 2x to the 7th. Once that graph is reflected, Now it's the right side that goes down. So as x goes to infinity, f of x goes to negative infinity. And the left side is going up. As x goes to negative infinity, f of x goes to positive infinity. And even as we add other terms to our polynomial, it is the leading term, the largest power of x, that's going to tell us what's happening at the ends of the graph. The other terms give us information about what's happening in the middle of the graph. So let's take a look at an example. Describe the end behavior of the polynomial f of x equals 3x minus x to the fourth plus 2x to the fifth plus 7x squared. So the first thing I have to do is identify my leading term. And the leading term is always the term with the largest exponent. So 2x to the fifth is my leading term. I have positive coefficient and an odd exponent. Positive coefficient, odd exponent means right side goes up. So as x goes to infinity, f of x goes to infinity. And the left side goes down. As x goes to negative infinity, f of x goes to negative infinity. Now, something else might be happening in the middle of the graph, and that is going to depend on the other terms in the equation. And it turns out that an nth degree polynomial, and the degree of a polynomial is that largest power. So for example, if I have the polynomial f of x equals 3x to the fourth minus 2x to the third plus x squared minus x plus 4, that leading term is 3x to the fourth. So I would call this a fourth degree polynomial. So an nth degree polynomial can have at most n x-intercepts and n minus 1 turning points. So this would be a fourth degree polynomial. This theorem is telling us that we can have a maximum of 4 x-intercepts. We might have fewer, but 4 would be the most we can have. And we can have a maximum of 3 turning points. Again, we could have fewer, it depends on the equation, but 3 would be the maximum we could have. So what that might look like visually, fourth degree polynomial with a positive leading coefficient, both ends would go up. It is possible, and again, this isn't guaranteed, but we might have 1, 2, 3, 4 x-intercepts, and we could have 1, 2, 3 turning points. Okay, so the degree of the polynomial gives us information about the end behavior and the maximum number of x-intercepts and turning points that we can have. But how do we actually find those x-intercepts? The first strategy that we're going to use, the strategy that we're going to use in this section, is to set the polynomial equal to 0. That's how we always find x-intercepts. And then try to solve. And factoring is a great strategy that we can use to solve polynomial equations. So my first example, I'm going to plug in 0 for y, and I get 0 equals 2x minus 3, x plus 1 squared. This polynomial is actually already in factored form, so I can set each of those factors equal to 0. Now this 2, this GCF of 2, that actually doesn't give me any x-intercepts because 2 cannot equal 0, so we could just ignore it. We don't have to write that down. But x minus 3 could equal 0, or x plus 1 squared could equal 0. X minus 3 equals 0, add 3 to both sides. I have a solution of x equal 3. That's one of my x-intercepts. X plus 1 squared equals 0. You could square root it to get rid of the squared. You're still going to have a 0, though, on the right. So if x plus 1 squared equals 0, well, x plus 1 must equal 0. Minus 1 from both sides, I get x equal negative 1. So this polynomial has 2 x-intercepts, one at 3 and one at negative 1. Let's take a look at a second example. To find the x-intercepts, I'm going to plug in 0 for y. So I've got the equation 0 equals x to the third minus 5x squared minus x plus 5. First thing I'm going to do is see if I can factor this. There are 4 terms, so I'm going to try the factoring by grouping method. If I look at the first 2 terms only, I have a common factor of x squared. If we pull out the x squared, we're left with x minus 5. Then I look at the second two terms only, and I notice I can take out a negative 1, and that will give me an x minus 5 as well. Because I have x minus 5 in both parentheses, that's like my GCF. I bring that out front, and I'm left with an x squared and a minus 1. This can actually be factored further. That x squared minus 1 is a difference of perfect squares. So I can factor this as x minus 5, and then the x squared minus 1 becomes x plus 1, x minus 1. Notice that I have a third degree polynomial, and I was able to factor it with 1, 2, 3 factors. I can set each of these factors equal to 0 and solve. If x minus 5 equals 0, x equals 5. If x plus 1 equals 0, x equals negative 1. If x minus 1 equals 0, x equals positive 1. So this was an example of a third degree polynomial that had exactly 3 zeros, or 3 x-intercepts, and those 3 x-intercepts corresponded to 3 linear factors. So zeros, or x-intercepts, correspond to factors. We can use that information to work backwards. For example, if I want to write the equation of a polynomial with zeros, and zeros are places where the function equals 0. In this case, these are x-intercepts. So my polynomial has zeros at x equal 1, x equal negative 2, and x equal 3. Each of these zeros must correspond to a factor. I'm just working backwards. So if x equal 1 is a 0, x minus 1 had to have been a factor. If x equal negative 2 is a 0, x plus 2 must have been a factor. And if x equal 3 is a 0, x minus 3 must have been a factor. So this polynomial in factored form would be f of x equals x minus 1, x plus 2, x minus 3. Sometimes you might be asked to give your answer in factored form. If so, that's it. We're done with the problem. If you're asked to give your answer in expanded form, that just means you have to multiply things out. So I started by foiling the x minus 1 and the x plus 2. First was x squared, outer 2x, inner negative 1x, last minus 2. And then I combined like terms. Those middle two terms, 2x minus 1x, gave me 1x. So again, I just multiplied x minus 1, x plus 2. I got x squared plus x minus 2. To finish, I need to multiply that trinomial by x minus 3. So I started by distributing the x to all 3 terms. That gave me x to the third plus x squared minus 2x. Then I'm going to distribute the minus 3 to all 3 terms. That gave me minus 3x squared minus 3x plus 6. Finally, if I combine like terms, we've got x to the third minus 2x squared minus 5x plus 6. And there is a polynomial with zeros at 1, negative 2, and 3. Now, one feature, one characteristic of zeros is going to play an important role to how we actually graph these functions. If a polynomial contains the factor x minus c to the p, then x equals c is a 0. So we just talked about that fact. If you have a 0, you must have a factor, x minus that number. If that factor has an exponent on it, that is the multiplicity of the 0. The multiplicity of the 0 basically tells us how many times do we see that exact same factor that gives us that exact same 0. So for example, if I have the function f of x equals x minus 2 squared times x plus 2. X minus 2 equals 0 when x equal 2, and x plus 2 equals 0 when x equal negative 2. This polynomial has 2 zeros, one at x equal 2 1 at x equal negative 2. Now the 0 of x equal 2 came from this factor x minus 2 squared. Because the factor is squared, that 0 has a multiplicity of 2. The x equal negative 2 came from the factor x plus 2. Now there was no exponent written there, but if you see a factor written just once, it's like there's an imaginary exponent of 1. The multiplicity of that 0 is 1. So why do we care about multiplicity? Well, if I graph this function, so I put this into a computer and I graph this function, notice that x equal 2 had a multiplicity of 2. Anytime a 0 has an even multiplicity, the graph is just going to touch the x-axis, or you can think of it as bounce off the x-axis. So x equal 2 had a multiplicity of 2, an even multiplicity, and so the graph is just touching the axes. X equal negative 2 had a multiplicity of 1. Anytime a 0 has an odd multiplicity, like 1, the graph is actually going to cross the axes. And that's what we're seeing happening at x equal 2. Or sorry, it's negative 2. So even multiplicities, the graph is touching the axes. Odd multiplicities, the graph is crossing the axes. So finally, let's put all of this information together, everything we've talked about, so that we can sketch the graph of some polynomials. So determine the end behavior, find the intercepts and their multiplicities, then sketch the graph. So for end behavior, I have a leading term with a positive coefficient and an odd exponent. That means the right side goes up and the left side goes down. Or as x goes to infinity, f of x goes to infinity. As x goes to negative infinity, f of x goes to negative infinity. Now to find my intercepts, or my zeros, I'm going to plug in 0 for y. So 0 equals 2x to the third minus 3x squared. And the very first thing I'm going to try is factoring. This problem has a greatest common factor. There's something that I can take out of both of the terms, and that is x squared. I'm going to pull an x squared out of both terms, and I'm left with 2x minus 3. Now I can set these factors to 0. X squared equals 0 means x equals 0. That has a multiplicity of 2 because it came from that x squared with that exponent of 2. 2x minus 3 equals 0. I add the 3, divide by 2. I get x equal 3 halves. That 0 has a multiplicity of 1 because I had only one factor of 2x minus 3. Now let's put this together to create a graph of this function. I think I'm going to label every 2 tick marks 1 unit just to give myself a little more space on my graph paper. And I'm going to start by graphing my zeros. I have an x-intercept at 0. This is actually my y-intercept as well. And I have another one at 3 halves or 1.5. So I plot both of my x-intercepts. And the next thing I'm going to do is I'm going to draw in my end behavior. So the left side of the graph has to go down. The right side of the graph has to go up. To fill in the middle of the graph, I'm going to think about these multiplicities. I know that at x equals 0, that has an even multiplicity. At x equals 0, the graph is just touching, so it's going to have to bounce back down. But at 3 halves, the graph is going to be crossing. And so I'm going to sketch something where at 0, it just bounces back down, and then it crosses at x equal 3 halves. And there's a rough sketch of that polynomial. Now, this is just an estimate. I actually didn't label my y-axes on purpose because we'd have to do some additional mathematics. This is actually a calculus problem if we want to figure out where that bending point is, where that turning point is. So we're just going to estimate. Your graph doesn't have to be perfect. I am just looking for end behavior and do you have your zeros in the right place, and the behavior of those zeros. All right, let's do another example. This time I have the function f of x equals x to the fourth minus 2x squared plus 1. First thing I'm going to do is find my end behavior. We have a fourth degree polynomial, so even exponent, positive coefficient. That means both ends go up. Or as x goes to infinity, f of x goes to infinity. As x goes to negative infinity, f of x goes to infinity. Both ends go up. To find my x-intercepts, I'm going to plug in 0 for y. So 0 equals x to the fourth minus 2x squared plus 1. Once again, my strategy is going to be factoring. This time I have 3 terms. So I'm going to draw my 2 parentheses and see if I can use some trial and error to factor this. Because the first term is an x to the fourth, when I fill in my parentheses, it's got to be an x squared and an x squared. That'll give me x to the fourth. Then I look at the last number. The last number is a 1. So I have to put in a 1 and a 1. And if I want the middle to add up to negative 2, they both have to be negative 1s. And we can check. Inner term is negative x squared. Outer term is negative x squared. Yep, that adds up to negative 2x squared. We can factor this further because x squared minus 1 is a difference of perfect squares. Each of those becomes x plus 1, x minus 1. So x squared minus 1 becomes x plus 1, x minus 1. Same thing happens with the second x squared minus 1, becomes x plus 1, x minus 1. I'm going to set my factors to 0. X plus 1 equals 0 when x equals negative 1. This 0 has a multiplicity of 2 because I have 2 identical factors that give me the same 0. X minus 1 equals 0 when x equals 1. This also has a multiplicity of 2 because I have 2 identical factors that give me the same 0. We could have also written those factors as x minus 1 squared and seen that exponent of 2. All right, so let's create our graph. I'm going to start by plotting my x-intercepts. They're at negative 1 and 1. And let's see, I should probably plot my y-intercept as well. My y-intercept, if I plug 0 into this function, I get 0 plus 0 plus 1. So my y-intercept is 1. Then to create my graph, I'm going to start with the end behavior. So both ends go up. The left side goes up, the right side goes up. To finish, to do the middle of the graph, I'm going to use the fact that both of my zeros have an even multiplicity. That tells me the graph is just bouncing off the axes or just touching the axes, not crossing the axes. So I'm going to draw my graph where it just bounces up the axes, comes back down, bounces off the axes again. And there's a rough sketch of what this polynomial looks like. Let's take a look at one more example. Find the equation for the polynomial shown in the graph. So now we're working backwards. The first thing I'm going to do is locate where my x-intercepts are. I have an x-intercept at 2 and another one at negative 1. Based on the behavior of the graph, I know that the x-intercept of negative 1 must have an odd multiplicity. The x-intercept of 2 must have an even multiplicity. So my polynomial has to be of the form f of x equals a times x plus 1. So this factor of x plus 1 is going to give me my 0 of x equal negative 1. I'm choosing an exponent of 1 so that I have an odd multiplicity. So 0 of negative 1 goes with x plus 1. We'll do an exponent of 1. X minus 2 squared corresponds with the 0 of 2. X equal 2 corresponds with a factor of x minus 2. The exponent has to be even. Choose the smallest exponents you can just to make the math a little bit easier for yourself. And then finally, we have to figure out what is this leading coefficient, what is the a value. To do that, I'm going to try to locate another point on the graph, and I can see that the y-intercept is located at 0, -4. So I'm going to plug those values into my function. Y is -4, f of x is -4, when x is 0. So I put zeros in for x, -4 in for f of x, and this is something that we can solve for a. 0 plus 1 is just 1, minus 2 squared becomes 4. Divide both sides by 4. -4 divided by 4 is -1, and I get a equal -1. That matches with what I see for the end behavior. The fact that the right side goes down and the left side goes up tells me that leading coefficient has to be negative. So plugging that in, there is my final answer. This graph matches the function f of x equals -x plus 1, x minus 2 squared. All right, that was my last example. As always, let me know if anything in this video is unclear.